Okay, so units and measurements, units and measurements. And if you have any query, then you can ask any question at any time. Okay, so units
Okay,
and measurements. So in physics, to define some quantities, we required its units. We required its unit. So what are physical quantities? Physical quantities. Physical quantities. Okay. So physical quantities are basically those quantities in which we define laws of physics. Okay, some laws of physics, such as on the basis of that physical quantities, we define laws of physics. So some physical quantities are basically fundamentals, fundamentals quantities such as length, mass. Okay, and some quantities which are derived quantities. So we derive these quantities on the basis of these physical quantity, on the basis of these fundamental quantities. Okay, so I'm going to clear what is the meaning of physical quantities. The physical quantities are those quantities, are basically those quantities, those quantities in terms of which, in terms of which the laws of physics can be expressed. The laws of physics can be expressed. Okay, laws of physics can be expressed. So the physical quantities are basically two types. The one is fundamental quantities, fundamental quantities, and the other one is derived quantities. Derived quantities. Okay, fundamental quantities. So fundamental quantities basically are these are basically independent of other physical quantities. These are very fundamental. Okay, so there are basically only 7 fundamental units. Okay, there are only 7 fundamental quantities, and derived quantities are those we use fundamental quantities to derive these quantities. Okay, so fundamental quantities, I'm just going to write one line about fundamental quantities, then we will discuss what are basically fundamental quantities. So these are independent of other physical quantities. These are independent of other physical quantities. Okay, other physical quantities. And derived quantities are basically may be expressed in terms of maybe expressed in terms of fundamental quantities. Quantities. Okay, the example of fundamental quantity, the example of the fundamental quantities is length, and mass, okay, and time, okay. So some are others I will discuss just after discussing what is derived quantities. So derived quantities, some examples of derived quantities such as force, okay, we represent force in terms of mass and acceleration, okay, and some as velocity, okay, etc. Okay, so up to now you have any question? Hello?
No, sir.
Okay, please write down important things, then I will go further. Okay. Okay. Should I go?
Yes, sir.
Okay. Yeah. What are you saying, Siddharth?
Yeah.
Okay. So
Nothing certain.
okay. So next thing is fundamental or base quantities. Now I'm going to talk in details about fundamental quantities. So fundamental or base quantities. Base quantities. Okay. So there are 7 fundamental or base quantity. The first one is length. The first one is length. Okay, length. So the SI unit of length, SI unit. What is SI unit? It, I am just here discussing what is SI unit. Okay, यहाँ पे लिख देते SI unit. ठीक है. SI unit we defined SI unit as International System of Units. International System of Units. System of Units. Okay. So this is the international system of units, means all over the world, these units are basically fixed. Okay. Every country follow these units. Okay. So if length, if we define length, so its unit, SI unit is fixed, which we define as meter. Okay. Its SI unit is meter. Okay. And we represent this meter as small m or L. The dimensional formula is L. Okay. The dimensional formula is L. Next, the second one is mass. The second one is mass. Okay. And its SI unit is kilogram. Kilogram. Okay. As kg. And its dimensional formula is capital M. Or we say dimensional representation is capital M. Okay. The dimensional representation of length is capital L, and the dimensional representation of mass is capital M. Okay. The next one is third is time. Okay. So the SI unit of time, what is SI unit?
Seconds.
Second, SI unit. And this is dimension. Okay. So SI unit is second, and we represent as small s, or the dimensional representation is capital T. Okay, dimensional representation is capital T. The fourth one is electric current. Electric current. Okay, which you will study in your next year. Okay, electric current, the SI unit of electric current is ampere. Ampere. Okay, and the dimensional representation of ampere is capital A. Okay, capital A. So length have dimensional representation capital L, mass have dimensional representation as capital M, time has dimensional representation as capital D, and electric current, which has SI unit ampere, has a dimensional representation as capital A. Okay, so next one is temperature. Fifth is temperature. Temperature. Okay, and the SI unit is Kelvin. Kelvin, and the dimensional representation is capital K. Capital K. Okay, so these are basically 5 fundamental units which you generally use in your 11th class. You know, in your 11th class, basically electric current. You will use this electric current in your 12th, most of it. But these one, length, mass, time, and temperature, you use in your 11th class. Mostly all the equations you will see, these quantities will come very usually. Okay, and the next one is 6th, which is amount of substance. Amount of substance. Okay, if you take any amount, so its SI unit is mole. Okay, and the dimension representation is again it's mole. Okay, MOL. Okay, and the next one, 7th one, the last one is luminous intensity. Luminous intensity. Luminous okay, wait. Luminous intensity. Intensity. Okay, so what is luminous intensity? By the using of this luminous intensity, we basically measure brightness of any object. Okay, and its SI unit is candela. Candela, and we represent dimensionally by CD. CD. Okay, so these are basically 7 fundamental or base quantities. We call these quantities as base quantities. Okay, so please write it down. Any questions, Siddharth, up to now?
So clear.
Okay, so should I go further? Or you are taking notes?
Yes, sir.
Okay, so next, these are 7 fundamental units, and there are 2 supplementary units. You know what are supplementary units? Supplementary units are those units which have units, but they don't have any dimensional representation. That's why we call these units as supplementary units. Okay, supplementary units. So there are basically two supplementary units. Okay, the first one is plane angle and the another one is solid angle. Okay, so next is supplementary units. Supplementary units. Unit. So there are two supplementary units. The first one is plane angle. Plane angle. Okay. Its SI unit is radian. Okay. Its SI unit is radian. What is plane angle? Plane angle is, suppose you move from a point A to B. Okay. You move from point A to B is something like as arc, as a arc. Okay. So if this is center of this arc and it's making angle theta. Okay, it's making it theta. Suppose someone is moving on a large circle. So this is a part of that simple large circle. Okay? The piece of a pizza. Okay. So this angle is basically theta. So the unit of this angle, we define this theta as arc, which is arc AB upon this radius r. Okay, so theta is equals to arc upon radius small r. Okay, so this arc upon radius r. So basically, this is the angle, plane angle. We call this theta as plane angle. Plane angle. Okay, this theta is plane angle. Okay, so the unit of this plane angle is radian. What is the unit of this angle is radian. Okay, so we often use this theta in our circular motion. When we study what is circular motion, and we define theta there, and there we use unit radian. Okay, radian. There is no dimensional representation of this radian. There is no dimensional representation of this radian. Okay, its SI unit is radian, but no dimensional representation. So another supplementary unit is solid angle. Another supplementary unit is solid angle. Okay, and the SI unit of this solid angle is steradian. Steradian. Okay, SI unit is steradian. And what is a solid angle? How you define a solid angle? So in two-dimensional plane, okay, in two-dimensional plane, when a body moves from A to B in an arc or in a circular path, okay. So if I use a three-dimensional representation, okay, not two-dimensional, a three-dimensional representation, such as, can you see this paper? Okay, can you see this paper, Siddharth?
Yes, sir.
Okay, so if I make a cone of this paper, wait a second. So this kind of geometry, when you see the cone of a ice cream, okay, this kind of figure. So this angle is solid angle. Solid angle. Okay,
Yes, sir.
it's a three-dimensional representation of plane angle. Okay, this is your solid angle. The angle at center point. This is your
Yes.
solid angle. So solid angle, the unit of solid angle is steradian. Okay. So these are some supplementary units. Supplementary. Okay. So 7 and 2 supplementary. So total 9. Okay. So on the basis of these fundamental units, we define derived quantities. Derived quantities. Okay. So all the other physical quantities can be defined on this 7 or total 9 fundamental units. Okay. So write all the important things so I can go further. Okay.
Yes.
Okay. Now let's define some derived units. Okay. Now some derived units. So we define derived units. A lot of derived units, Fundamental units are basically 7, but all the other physical parameters can be defined on the basis of these fundamental units, such as the first one. Next I'm going to discuss derived units. Derived units. Okay. So first one, area. Okay. So how you define area? What formula we use for area? Area is defined as length into breadth. Okay, length into breadth. Okay, L into B, which is L into B. Okay, so L. So what will be the unit for area? L has a unit meter. Okay, and B has a unit in meter. Okay, meter. So the unit of area is meter square. Is it clear?
Yes, sir. Clear.
Okay. So the dimensional representation, this is the unit of area, which is meter square, and the dimensional representation. So how what is the dimensional representation of meter? What a symbol I used?
Sir, can you repeat?
Now, what is the dimensional representation of length or meter? As I discussed just before, the first fundamental unit which I discussed, length. What is the dimensional representation? Just go up. Remember, I use capital L here.
Yes.
For length meter, I use capital L.
M.
Not M, capital L. L is M for meter. M for meter. This capital L is the representation.
Yes,
Capital
sir.
Okay. Capital M is for mass. So if capital L is the representation of this length, okay, which is meter. So here meter yani L and another meter. So L the whole square. Is it clear?
Yes, sir. Clear.
Clear now? If you have any doubt, then please ask, because this is a very simple derived units. Okay, we will do some difficult one, but first understand the simple one. Another is volume. Okay, volume. So how you define volume? Length into breadth into height. Okay, length into breadth into height. So formula is L into V into H, and the unit for L is meter, and again B for meter, and again H for meter. So 3 meters, and this will be a meter cube. Okay, so length has a unit meter, breadth has a unit meter, height has a unit meter. So its total unit is meter cube. So this is a unit of volume. And what is the dimensional representation? The dimensional representation of volume is L cube. Okay.
Yes.
L cube. I write L cube. That's better. L cube. Okay. And here square is inside the bracket. L square. Okay. The volume area. So next, third one which I'm going to discuss is velocity. Velocity. Okay, so how you define velocity? Siddharth, do you remember what is the formula for velocity? How we define velocity?
Yes, sir. Velocity velocity formula is
Okay.
displacement by change in time.
Okay. So okay, velocity is your displacement upon time. Okay. So we defined displacement by meter, because we are talking only for units. So displacement have unit meter and time is second. So it's a unit is meter per second. It's a unit. And how we represent this velocity in terms of dimensions, yani dimensional representation. So
L by T.
L by T, very good. So L by T. So the standard form to writing this L by T is LT minus 1. Okay. I just put from numerator to denominator by using a minus sign. Okay. When T comes with L, so its sign goes +1 to -1. Is it clear?
Yes.
L by T, we can also write this L by T as LT minus 1. Okay. Next, acceleration. Fourth one is acceleration. Okay. Okay. First, write all the things. Are you taking notes or not?
Yes, sir.
Okay. Okay. So have you written write down all the things so I can go?
Yes, sir. Done.
Okay. Acceleration. We define acceleration as
velocity by time.
Velocity by time. Velocity by time. Okay. So velocity by time, and again the unit of velocity is meter per second, and again per time. So the unit for acceleration is meter per second square. Okay. And the dimensional representation, what will be the dimensional representation? Dimensional representation of acceleration is L by T square. Okay. So we can also write this as LT minus 2. Okay. Okay. So why we are using this dimensional representation? Dimensional representation basically says that we can represent acceleration in terms of length, 1 unit in length and -2 unit in time. Okay, such as velocity, 1 unit in length and -1 unit in time. Such as volume, 3 units in length. We can define volume as 3 units in length. Okay, so this is the meaning of this dimensional representation. Next one is momentum. Actually, I'm calculating all the units and dimensional representation of some very useful derived quantities, derived physical quantities. Okay. So next one is fifth one is momentum. Okay.
Mass into velocity.
Okay. So very good. Its formula is mass into velocity. Okay. So mass, what is the unit for mass? Kilogram. And velocity, we just calculated meter per second. Okay. So this is a unit. And what is a dimensional representation? Dimensional representation of this momentum is kilogram is mass, m, capital M, meter is length, capital L, and second is T divided by T. So it's LT minus 1, MLT minus 1. Okay, momentum. Okay.
Yes, sir.
Clear? If you have any doubt, then you can ask any question anytime. The next one is force. This unit is very important. Force. You have to remember the dimensional formula for force. It will be very useful to finding other derived quantities. The very important formula is for force. Okay, always remember what is the unit and dimensional representation of force. Always remember. Okay, this will be very helpful. Okay, very helpful. So the special unit force, I am marking a star.
Mass into acceleration.
The formula is mass into acceleration. Mass into acceleration. And so the unit is mass kilogram. And as we discussed before, the acceleration, the formula of the unit of acceleration is meter per second square. Okay, so this is a unit, this is SI unit, and we define this kilogram meter per second square as Newton. Okay, Newton as capital N. Okay, Newton. So you can also say kilogram meter per second square or Newton. What is the dimensional representation of this force? Dimensional representation. So dimensional representation is kilogram as a representation capital M, meter as a representation L, and per second square. So I can write this T minus 2, MLT minus 2. Okay. So this is a dimensional representation. This dimensional representation is very important. Always remember these things, you know, what is the unit of force and what is the dimensional representation. If you know the formula of this force is equals to mass into acceleration, then you can easily find out what is the unit and dimensional representation. But if you remember, then it will be also very useful for you. Okay. Okay, clear? Is it clear?
Yes, sir.
Okay. Next one is walk. Seventh one is walk. Okay. So the formula for work is force into displacement. Force into displacement. Now it's very useful. As I say, the unit of force is kilogram meter per second square. Okay, and into displacement. What is the unit for displacement? Hello?
I guess displacement unit is meter.
Okay, again meter. So the unit for work is kilogram meter is square per second square. So this is the SI unit for work, kilogram meter square per second square. So we define this kilogram meter square per second square as joule. Okay, so either you can write kilogram meter square per second square, or you can also write joule. Joule is also SI unit of work, such as Newton is SI unit for force. Same, joule is a SI unit for work. Okay, so I think this is a very lengthy representation, kilogram meter square per second square. So people start representing this by as a joule. Okay, so joule. Now what is the dimensional representation? Dimensional representation. Okay, so as you know, force we define force as ml t minus 2. Okay, into displacement meter, so it's into L. Okay, so again this is m L square t minus 2. This is the dimensional representation. Okay,
Yes, sir.
Okay. So next one is after work. We are going to energy. Energy. It's energy. Okay. So energy, we can also find the dimensional representation for energy such as kinetic energy or potential energy. But here I'm talking about energy. Generally, we define energy as it's the amount of work done. It's the amount of work done. Amount of work done. So amount of work done. So the unit of energy is same as work done. Okay. So as you know, we also define the unit for work is joule and unit for energy is also joule. Okay. So we will discuss briefly the relation between work and energy in our next chapters. Okay. Work, energy and power. Okay. So here I'm just discussing what is the unit and dimensional representation of energy or work. So we define the dimension, the unit of energy is again same as work, which is kilogram meter square per second square, which is again joule. Okay, and the dimensional representation same as work. Dimensional representation is ml square t minus 2. Okay, so this is a very important thing. You can also remember that the dimensions of work and energy is same. The dimensions of work and energy is same. Okay. Okay, so I can write here the dimension and unit of work and energy is same. Write it down. Okay. Okay, is it clear?
Yes, sir.
Yes.
Okay. So next one is ninth is kinetic energy. Kinetic energy. Kinetic. So the formula for kinetic energy is half m mass into velocity square. Okay, mass into velocity square. So intuitively, can you say what is the dimension, what is the unit of kinetic energy? So the unit of kinetic energy must be same as energy. So it must kilogram meter square per second square. But okay, we can also calculate the unit of this kinetic energy by this formula, which is half mass into velocity square, which is half mv square. Okay, let's leave this half. As we know, the formula for mass, the unit of mass is kilogram and velocity is meter per second and the total is square. So again, it's kilogram meter square per second square, which is same as dimension of work and energy, and which is joule, Okay, and again dimensional representation is also same as work and energy, which is ml square t minus 2. Okay. So these are basically after force, all the quantities which I discussed, such as energy, kinetic energy, force, work done, are basically important. Okay. Okay.
Yes.
Okay. So I'm going on the next unit. So am I going fast or is it okay?
It's okay.
It's okay now?
Yes, sir. Good only.
Okay. Next 10th one is next is pressure. 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 So we define pressure by force per unit area. Area. Okay. The force acting on area. So define the force acting on area defines pressure. So what is the unit of this pressure? We talk about unit. So unit force, the unit of force is kilogram meter per second square. And what is the unit of area? The unit of area is meter the square. Okay, meter square. So here you can see that this meter and this meter cancel out. Okay, so I just cancel this meter and this meter. So what is the remaining terms is kilogram per meter into second square. So this is the unit for pressure. Is it clear?
Yes, sir.
Kilogram meter per second square divided by meter square. So 1 meter cancel out. So kilogram per this denominator term meter, this denominator term meter second square. So this is a unit for pressure. This is the unit for pressure. Okay. And next the dimensional representation. Dimensional representation. Can you find? I discussed a lot of derived units. Can you find what is the dimensional representation of this pressure?
Yes, sir.
Please try.
Sir, is it M1 L1 T minus 2?
Yes, M1 L1. Okay, so there is a correction. Dimensional representation. Kilogram is the dimensional representation of kilogram is capital M. Okay, and divided by meter has a representation capital L, and second has T square. So the dimensional representation is M capital L raised the power -1, T raised the power -2. So it's ML -1, T -2. Okay. Okay, clear?
Yes, sir.
Okay, is it clear to Fatima?
Yes, sir.
Okay, if you have any trouble, then you can ask. Okay, so this is the unit for pressure. Now next one is next unit is impulse. Impulse. Okay, I will briefly discuss what is impulse in our next chapters, but for unit and dimension representation, I'm just using its formula. So the formula for impulse is when a force acting for a short time, when a force acting for a short duration, such as a car hits a truck, okay, or two billiards ball hits each other. So for a momentary, they apply basically a force for a very short interval. Okay, so impulse, the formula for impulse is force into time. Force acting for very short duration, force into time. So here we are interested only to find the unit and dimension of this impulse. So the unit of this impulse is force. We define force as first unit. So unit is force have a unit kilogram meter per second square into second. So this second cancel out. So the unit of impulse is kilogram meter per second. Unit of impulse is kilogram meter per second. Okay, kilogram meter per second. And what is the dimensional representation? Dimensional representation. Okay. Next, try
M1
ah,
M1 L1 T minus 1.
exactly. So kilogram has M, meter has L, and divide by second, so T minus 1. ml T minus 1. Okay, so these are some basically some derived units. Okay, so most of them I discussed. Okay, some another one which I will discuss later. Okay, so these are basically derived units. I think both of you, I think, are able to find the unit and dimension representation of some very basic physical derived units. Okay, such as
Yes.
force, energy, and etc. etc. Okay, so now let's go to the another part of this topic. Okay, let's go to the another part of this topic, which is application of this this units, you know, this dimension analysis. So next thing, put a heading over your copy, is application of dimensional analysis, where we can apply this dimensional analysis and what is the use of this dimensional analysis. So next thing is application of dimensional analysis. Okay, so there are basically three major application of dimensional analysis. Okay, the first application of dimensional analysis is to convert a physical quantity in some another units. Okay, the first one is to convert a physical quantity to convert a physical quantity from one system to one unit system, from one system of units to other. Okay, so for example, we define unit of length is meter. We define unit of length is meter, but there is another unit of length is centimeter. Okay, so we can convert this unit, SI unit meter, to CGS unit centimeter. Okay, so this is the first application, that you can convert units in another unit system. Okay, so it suggests meter to centimeter. Is it clear?
Yes, sir.
And another application of this dimension analysis is you can find the correction of given physical relation. To find the correctness of a given physical relation. Okay, so suppose you have a relation and you want to check is this relation correct or not? Dimension analysis can help to find the correctness of any physical relation or physical equation. Okay, suppose you have equations such as v is equals to u plus at. Okay, so this is the first equation of motion. So v is equals to u plus at, and suppose someone says v is equals to u plus at plus x. Is it correct or not? So I will discuss this equation. So by the use of this dimensional analysis method, you can exactly say that is it equation correct or not. Not exactly. Okay, there is some drawback of this dimensional analysis, but I will discuss this. But in most of the cases, you can basically define the by use of this dimensional analysis, the equation is correct or not. Okay, the equation is correct or not, to find the correctness of a given physical relation. And the third one, okay, third one is to derive a relationship, to derive a relationship, to derive a relationship between physical quantities, between physical quantities. Okay, so suppose two quantities have some relation. Two quantities have some relation, such as area has a relation with length and breadth. Okay, so suppose there is a relation between two quantities. Suppose someone is force, and forces depends on mass, forces depend on acceleration. But you don't know how this relation take place. How what are basically the exact equation. Such suppose force depends on distance. Force depends on distance, and force also depends on mass, but it may be reciprocal term, it may be in denominator term or numerator term, it can be anywhere. Suppose force depends on mass, force depends m, okay, and force is also depends on distance, yeah, r. Okay, but you don't know, okay, what is the exact format of this force. So by the use of this dimensional method, you can find that F is proportional to m square by r square, something like this equation. Okay, so that is basically the formula for gravitational force, G capital M small m by r square. Okay, so I will discuss this formula in details in chapter of gravitation, but here only for discussion purpose, that two physical quantities are have some relation, and to find the exact relation we use dimensional analysis method. Okay, so there are basically three major application of dimension analysis. Is it clear? Hello, is it clear or any doubt?
Yes, sir, it's clear.
Okay, so please write all the important things.
Done, sir.
Done. Okay, and another.
Sir, how do you actually find the relationship between them by using this dimensional?
Okay, all the three applications I'm just going to discuss in brief. All the three. Okay.
Okay, sir.
Okay. This is just introduction where you can apply this dimension analysis. Okay. Just wait. I will discuss all the things. So first, I'm going to start how you can find the correctness. The second one. I'm going to start with second one. That's, I think, more easy. Okay, so you can change number. So how you can find the correctness of equation, the equation is correct or not. Okay, so there is another name of this application is homogeneity of dimensions. Okay, homogeneity of dimensions. Dimensions in an equation. Or you can also say to find the correctness of any equation or physically derived units or quantities. Okay, so to find the correctness of a given physical relation or physical quantities. Okay, so homogeneity of dimensions in an equation. So the homogeneity of dimensions of an equation. Okay, so what is the homogeneity of dimensions of equation? Let me very clear to you that in physics or in our real life, we only subtract or add same thing. Okay, you can't subtract time with mass. You can't add time or mass, because this time and mass, these are two different physical quantities. Okay, is it clear? Okay, is it clear? Because this is
Yes,
very
sir.
very basic concept, that similar quantities add or subtract similar quantities. Okay, similar, you can't add length, length with time, or length with mass, because these are two different physical quantities. So similar quantities add or subtract. Similar quantities add or subtract. Okay, for example, we cannot add velocity with force, or for example, we cannot add or subtract mass with time. Okay, similar quantities add or subtract. So this simple principle is basically defined as homogeneity of dimension. And throughout a equation, the dimension will be homogeneous. Similar quantities add or subtract. Okay, so this principle is called principle of homogeneity of dimension. This principle is called homogeneity of dimensions. Homogeneity of dimension. Okay, now let's take example. Suppose I take equation x is equals to ut plus half at square. Suppose I ask, what is this equation? This is a simple equation of motion. This is a simple equation of motion. Okay, I think both of you is familiar with this equation. Huh?
Yes, sir.
Have you seen before?
Yes.
Okay, so this is equation of motion. I think it's a second one. So x is equals to ut plus half at square. Okay, so left hand side, this x is basically displacement. This x is basically, what is this x? This x is displacement. This, okay, I have to write in large way. So x is equals to ut plus half at square. Okay, so here x is displacement. Here x is displacement. Displacement. Okay, so what is the unit for displacement? What is the unit for displacement? It's a meter. Okay, and the dimensional representation is capital L. Okay, so this principle says that the unit in left hand side, which is x, so all the term in equation must have unit or dimension same as x. Yeah. So here the unit is x have meter, so this term ut must have unit meter, and this 80 square must have unit meter, so that these two quantities can add. Okay, if any term ut or 80 square don't have the unit meter or dimension L, so this equation is incorrect. Okay, let's check it out. Ut have the dimension meter, ut have the unit meter or not. Okay, so u, what is u? U is initial velocity. Okay, what is u? U is initial velocity. So what is the unit for velocity? Initial or final is velocity, so unit will be same. What is the unit of velocity? Is meter per second, and here t is time, so again second, so second and second gets cancelled out. The unit of this ut is meter. Okay, is it clear? Hello?
Yes, sir.
Okay, next 80 square. Okay, in unit system we don't consider the constant. 80 square, so a here is acceleration, and the unit of acceleration is meter per second square, and here t, the unit of t is second square. So this second square cancel out, so the unit of this term is meter. So as you can see, left hand side the term x has unit meter, so in right hand side the first term ut has unit meter, and the second term, which is 80 square, half 80 square, is again unit meter. So you can say that the dimension is homogeneous in this equation. Dimension is homogeneous in this equation. So left hand side each term has unit meter, and right hand side each term has unit meter. So this equation is balanced, dimensionally balanced. So this equation is correct. Okay, is it clear?
Yes, sir.
Okay, so let us take another example if it is not clear. First, write all the things, right? Take a note. Okay, take a note so I can go further. Okay, Fatima, is it clear or you have any doubt?
No, sir, it's clear.
Okay, it's clear. Okay, have you done all the guys?
Yes.
Okay, so next example I'm taking another equation, which is v square, which is another v is equals to the easy one, u plus 80. Okay. If I ask this equation is correct or not, dimensionally correct or not, so as I discussed, the unit in left hand side is same as units in each and every term of right hand side. So the unit of v here, v is velocity, final velocity basically, but its velocity, the unit will be same. So the unit of velocity is meter per second. So this is a necessary condition that each and every term, means you have the unit meter per second, and this 80 term must have the unit meter per second, then and only this equation will be correct, dimensionally correct. Otherwise this equation is not correct. Okay, So this is one of the main application of dimensional analysis, that you can check the dimension, you can check homogeneity of dimension and say that this equation is correct or not. So this final velocity has a dimension meter per second. Okay, so this is correct. Okay, this is correct. Okay, and another AT. So AT, here is acceleration. So the unit of acceleration is meter per second square. And what is the unit of t? Is second. So second and second cancel out. So remaining unit is meter per second. Okay. So here you can see left hand side V has a unit meter per second, and right hand side first term as a unit meter per second, and the last term has unit meter second. So this equation is dimensionally correct. This equation is dimensionally correct. Okay. Okay. So let us take another example. Third example. Next thing. Third example. Okay. Third one is V square is equals to U square plus 2AS. Okay. Here S is displacement. S is displacement. Okay. And V is initial final velocity and U is initial velocity. So please guys check it. Check this equation. Is it correct or not dimensionally? And try once. Okay. Try once by yourself that is this equation is correct or not dimensionally.
Sir, the equation is correct.
Equation is correct. And Fatima?
Yes, sir.
Okay. So this equation is correct. Okay. So let me explain. Okay. Let me explain to you so that you can check your answer. So here velocity, left hand side has velocity. So velocity has a unit meter per second and it's a square. So right hand side, each and every term must have the unit this meter per second square. Otherwise this relation is not correct. This equation is not correct. So first term is quite easy because it's final velocity. So it's velocity. So unit will be same. So the unit is meter per second ka square. And here this term, we can neglect this term too. A is acceleration. A is acceleration. So acceleration has a unit meter per second square. Into S. S has the, as I said, S is displacement. So the displacement has unit meter. So the second term has a unit meter square divided by second square. So each and every term have same unit. Here this has meter per second ka whole square, meter per second ka whole square. यहाँ भी here is also meter per second का square. Okay, meter per second का square. So this unit is correct, dimensionally consistent. Okay. Okay. There is one limitation of this method. There is one limitation. So you can write the limitation. The limitation. There is a limitation of this equation. So here I'm discuss the limitation. Limitation. Okay. Limitation. So dimensions of the problem is in this equation is that the equation S is equals to UT plus half AT square is correct, dimensionally correct. Okay, and by using same formula, you can also say that S is equals to UT plus 2AT square. This is also correct dimensionally. Correct dimensionally, but this equation is not correct because practically this two term will create a trouble because the exact relation is half AT square, not 2AT square. But dimensional formula says that okay, this is also correct, but practically it is not correct. So this is the limitation. Okay, so because why this limitation come? Because dimensions does not depend on magnitude. Dimension does not depend on magnitude. Here half term and two term basically are not contributing. So half is also correct, 2 is also correct, but practically is 2 is not correct for this equation. Okay, so you can write a statement that dimensionally correct equation. You can write a statement dimensionally correct equation need not to be correct, okay, but dimensionally incorrect equation, incorrect equation must be wrong. Okay. Okay, so this is one of the application which is homogeneity of dimensions in equation. So any question related to this concept, homogeneity of dimensions of an equation? Any question?
No, sir.
And Fatima, do you have?
No, sir.
Okay. So now let's go to the another application which is conversion of units. Okay. Next application which is conversion of units. Next one is conversion of units. Okay. So basically, there are mainly two systems in physics: SI unit system and CGS unit system. SI unit system is CGS unit system. SI unit system. Okay. To CGS unit system. CGS unit system. Okay. But always remember this point that the magnitude of physical quantities doesn't change in any unit system. Okay. Suppose in SI unit you represent mass as 1 kilogram. So in CGS unit system you will define it's 1000 gram. But magnitude doesn't change. Either you can say it's 1 kilogram or you can say 1000 gram. The magnitude will be same. So the magnitude of the physical quantity remains the same. Magnitude of the physical of the physical quantity remains the same. In any unit system, either it is SI unit system or CGS unit. So SI unit system, there is another name of SI unit system. SI unit system, there is another name of this SI unit system is MKS. Okay, MKS. Okay, it's another SI unit system, and this is CGS unit system. Okay, this is SI. So in SI unit system, we basically define mass by kilogram, length by meter, and time by second. In SI unit system, we define mass by kilogram, okay, as I discussed, and length, okay, by length by meter, and time by second. Okay, second. So that's why it's MKS. M for meter, K for mass, for K for kilogram, and time for second. That's why it's another name is second, MKS. Okay. And CGS unit system, if I say CGS unit system, CGS unit system. CGS unit. So CGS here, in CGS we define mass as gram, okay, and length. Anyone? What is the unit of length in CGS? Anyone?
Centimeter.
Centimeter. Okay, very good. Centimeter. But the unit of time is same in both CGS and SI unit system. Time has second. Okay, time has second. So the conversion of this SI to CGS unit or CGS to SI, basically we will learn in this topic. How you can convert a physical quantity from SI unit to MKS CGS unit, and from CGS to SI units. So there are basically two famous examples which I will discuss in this topic. Two famous examples. One example is how to convert 1 dyne into Newton, okay, or 1 joule into arc. Okay, first thing. Have you taken the note of this this topic? Okay, wait a second. Conversion of units. Should I go further? Okay.
Yes, sir.
Okay. So the first example which I am going to do of this conversion is convert 1 joule into arc. ERG. Convert 1 joule into arc. Okay. So as I discussed before, joule is a unit of energy. Joule is a unit of energy. So we define 1 joule as kilogram meter square per second square. Okay. So let's convert this 1 joule into 1 joule. Joule is a SI unit, and erg is a CGS unit of energy. Okay. Joule is a SI unit of energy, and erg is a CGS unit of energy. So you can write here joule is a SI unit of energy and erg is the CGS unit of energy. Okay, so let's convert this joule into erg. So 1 kilogram. So 1 kilogram. So you have to convert this 1 kilogram into gram. Okay, CGS unit of mass, which is gram. So 1 kilogram into gram. So what is the value exactly? 1 kilogram into gram. It's 1,000 gram. 1 kilogram has 1,000 gram. Na? 1 kg is equals to 1,000 gram. Na? All of you, I think, familiar with this conversion. 1 kilogram is equals to 1,000 gram. This is a very basic thing. Na? Okay. Hello. Hello.
Yes, sir.
Okay. So 1 kilogram is 1,000 gram. And again, meter. So you have to convert meter into centimeter. Okay. So here 1 meter is equals to 100 centimeter. Okay. Okay. Is it all of you, I think, familiar with this conversion? Na? 1 meter is equals to 100 centimeter. Fatima? Hello? Hello?
Yes, sir.
Fatima, are you listening?
Yes, sir.
Are you familiar na, with this kind of conversion? Or you have trouble?
No, sir.
Okay. So that I can go little fast. So meter, 1 meter has 100 centimeter. 1 meter has 100 centimeter. So you take 100 centimeter square and divide with second. You don't need to convert second. You just need to convert this kilogram and meter into gram and centimeter. Okay. So what is the value? What is the exact value? What is the exact value? So 1,000 gram. Next 1,000 gram. There is a whole square. So what will be this 100? This is the square of 100 is 10,000. 1, 2, 3, 4 centimeter ka square divided by second square. Okay. So how much zero here? Basically 4 here and 3 here. So total 7. Okay. So I can write 10 raised the power 7. And this is gram. So I can write here gram centimeter square per second square. Okay, is it clear? Or you have any doubt?
No, sir. Clear.
Not clear now. So here you convert this joule into arc, and here what is result? So here 1 joule is equals to 10 raised the power 7. है ना? 1 joule. I can also write this 1 kilogram meter square per second square. This is SI unit and this is CGS, gram centimeter square per second square. So this is 1 joule basically is equals to 10 raised the power 7 arc. Okay, so this is our result basically. Yeah, so I can box it. Okay, so this is the conversion of 1 joule into arc. This is the conversion of 1 joule into arc. So this is the example of dimensional analysis. You can convert this, or another, you can convert this arc into joule. You can also convert this arc into joule. So what will be the result? 1 arc is equals to 10 raised the power minus 7 joule. Okay, so you can take the reverse process. Okay, similarly, you can convert arc into joule. Okay. Okay, should I scroll? I'm going to scroll down. Okay.
Yes, sir.
Okay, sir.
Okay. So you can also convert this 1 arc. This is for your homework problem, is equals to 10 raised the power minus joule. Okay, you just have to reverse the process, you will get the exact result. Another example, another very good example of this topic, conversion of unit, is convert 1 dyne into Newton. Okay, you can you will see there is a complicated method over a book that you have to do a lot of things. You just need to convert kilogram into gram, meter into centimeter. That's it, and you will get your result. Okay, just convert to kilogram into gram and meter into centimeter. You will get your desired result. Okay. So another example of this problem is convert 1 dyne into Newton. Yeah, 1 Newton into dyne. Next problem is convert 1 Newton into dyne. Okay. So what is the unit of force? You know, as I discussed, unit of force is Newton. Unit of force is SI unit of force. SI unit of force is Newton. Okay. And what is the CGS unit of force? The CGS unit of force is dyne. Yeah, you can also use small letter dyne or Newton. Okay, so these are the units of force. The SI unit of force is Newton and the CGS unit of force is dyne. Okay, and now you have to take a conversion from this SI unit to CGS unit, from Newton to dyne. Okay, so 1 Newton. Okay, so how you represent Newton? How you represent this Newton? So Newton is nothing but it's 1 kilogram meter per second square. So in this way you can define 1 Newton as kilogram meter per second square. Okay. Okay. So yes, this is a unit of Newton. Now you have to convert kilogram into gram, meter into centimeter, and you will get your desired result. So here 1 kilogram. So kilogram, what is, if you convert kilogram into gram? So as I discussed earlier, that kilogram has 1000 gram. Okay, and meter has 100 centimeter. And you don't need to convert this second. You just write second as it is. So how much zeros here? 3 this side, 2 this side. So total number is 325. So we can write this 10 raised the power 5 and this gram and this centimeter per second square. So this the SI system. In the SI system, you define Newton as kilogram meter per second square, and in CGS system, you define gram centimeter per second square. You convert kilogram into gram, meter into centimeter, and second as it is second. So in this way, you can define as 1 Newton is equals to 10 raised the power 5, and this quantity, which is gram. Okay, let me clear all the things. So this value basically 1 kilogram SI unit 1 kilogram dash meter per second square, which is nothing but 1 Newton, is equals to 10 raised the power 5 gram centimeter per second square. So we call this thing as 1 Newton is equals to 10 raised the power 5 dyne. Okay. So this is another example of conversion of this unit. Okay. Take a note. Take a note. 1 Newton is equals to 10 raised to the power 5 down, 5 Dan. So this is another example. This is another application of dimension analysis. Any question, any doubt, any query related to this topic?
No, sir.
Okay. So now I'm going to discuss the last application of dimension analysis. Okay. The last application of dimension analysis. And after this last application, your topic of dimension analysis will be over. Okay. So the last application of dimension analysis, finding relation between physical quantities. Okay. The last next application of this dimension analysis is finding relation among the physical quantities. Finding relation among the physical quantities. Okay. Again, in this topic, I will discuss 2 examples. And these 2 examples are very important. These 2 examples are very important. Okay. So these are very famous example, and most of the times teacher asks question from these 2 examples. Okay. And if you clearly understand these 2 examples, then you can solve any problem related to this topic, like you can find any relation, okay, by using this this method. Okay. So first example is, if force, as I discussed, force depends on m, and force depends on velocity, and force depends upon on r, but we don't know how this relation, means here a, b, c are unknown. We don't know what is value of a, b, c. This relation of force, maybe F is equals to m v square r cube. This relation may be F is equals to m cube v raised the power 1 r raised the power 2. So there are many ways to represent this formula. We don't know what is the exact values of ABC. What is the exact value of ABC? So we by finding this exact value of ABC, then and only then we can say that we can find the exact form of this force by finding the values of ABC. The problem is we have to find the exact value of A, B, and C, so that we can get the formula of force, formula for force in the above equation. Okay. Is it clear? Problem is clear. what is the problem? We know F depends on M, we know F depends on V, we know F depends on R. But in which way it depends, we don't know. Okay. A, B, C are unknown. We have to find what is the value of A, what is the value of B, and what is the value of C. Okay, is it clear? Problem is clear? Hello?
Yes, sir.
Siddharth? Are you
Yes,
there?
sir.
Okay.
Yeah, sir, I'm there.
So let's try to solve this problem by using dimension analysis. So here, left-hand side is force. Left-hand side is force. Here, F is force. Again, I'm rewriting the equation. Solution. This is the solution of this problem. F is equals to m raised the power A. Here, m is mass. V raised the power B. Here, V is velocity. And R raised the power C. Here, R is the basically distance. So F is force. As I told you that always remember what is the dimensional formula for F. So the dimensional formula for F is m L T minus 2. Always remember the formula for F. This will be very useful. Most of your problem in physics will be solved by only remembering this. All the dimensional problem will solve by remembering this formula of F. Okay. So this is ml t minus 2, and here m is again mass. So here capital M raised the power A, and V is velocity. So the dimensional formula for velocity is L t minus 1 the whole the power B, and R is again it's a distance, so it's L raised the power C. Is it clear? Anyone?
Yes, sir.
Fatima, any problem in this step? I just wrote only the dimensional representation of force, mass, velocity, and nothing else. Okay.
Yes, sir.
Okay. So here in left hand side m L t minus 2, and here right hand side we can say m raised the power A, L raised the power B, T raised the power minus B, because LT minus 1 the power B. Okay, LT minus 1 the power B. And here next step, next parameter is L raised the power C. Okay. So L raised the power B, T raised the power minus B, L raised the power C. So here capital M raised the power A, and here B and C. There are two terms of L raised the power B and L raised the power C. So here L raised the power B plus C. Okay. Here L raised the power B plus C. Now, is it clear?
Yes, sir.
L has power L raised the power B, and there is a common term L raised the power C. So we just add this L into L, so power will be added. Power will be added. In multiplication, power will be added. Okay. And another term, T raised the power minus B. We just have to find the value of ABC, remember, okay? And in left hand side, it is M L T minus 2. Now everything is set. You can find the value of A, B, C by comparison. Okay. Okay, if we compare this left hand side to right hand side, then we can easily find that mass is totally independent with length and time. Mass is totally independent with length and time. So power of M will be power of M. We can compare power of M in both the sides, left hand to right hand side. So if we compare the power of M, so we can find here M has a power A, and here M has a power. What is the power of M here? In right hand side, what is the power of M? Anyone? Here, what is the power of M in left hand side? Siddharth? Hello?
Yes, sir.
What I'm asking, what is the power of M in left hand side here in this part?
-1.
No, here m. M has power 1, na? Only 1.
Oh, yes, sir.
L is 1 and T is -2. So if we compare m raised the power small a and here m raised the power 1. So from here, by comparison, we can find a is equals to 1. Is it clear?
Yes, sir.
है ना? Fatima, is it clear na? Hello?
Yes, sir.
हाँ. Acha, you get the value of 1 a. Now another, if you compare L, so here L raised the power b plus c and here L raised the power 1. So here you can get value b plus c is equals to 1. Okay. So you get another equation. And the last one, from here you can find by comparison of t. Here t has a power -2 and here t has the power -b. So here you can have -b is equals to -2. So here you get the value of b is equals to 2. So you have value a is equals to 1, you have value b is equals to 2. Okay. So you can find the value of c. So if I put this value of b in this equation, so we can have 2 plus c is equals to 1. So here the value of c is equals to 1 minus 2 and this is -1. So by using dimensional analysis, we exactly find the value of ABC. We just compare dimensions left hand side to the right hand side. Okay. Okay. So we get the value a is equals to 1, b is equals to 2 and c is equals to -1. Now let's put these values in our original formula. Okay, let's put this value. So what was the equation? Equation was f is equals to m raised the power a, v raised the power b, and r raised the power c. So if we put the values, so m raised the power 1, v raised the power 2, and r raised the power -1. So this is the formula. F is equals to, now we know exact formula is m v square by r. Okay, this is the formula for force or centripetal force. This is the formula for centripetal force. So this is our result. Okay. So should I explain it again?
Sir, for me it's clear.
Huh?
Sir, for me it's clear.
Okay, sir.
For Fatima, should I repeat it again?
No, sir.
No, is it clear? So
Yes.
okay. So I'm going to discuss another example, and that will be the last example of this topic. And I think most of the thing I covered of this dimensional analysis. Next formula, this is again a very famous formula. Okay, so this centripetal force which I discussed basically when a body moves in a circular motion, then it experiences a force inward direction. And that force is basically centripetal force, and its value is mv square by r. Okay. Here I just discuss it dimensional method. What is the physics behind it? How this formula comes? I will discuss in another chapter. This chapter is only belongs to the dimensional values, dimensional representation, and unit systems. There is another formula which can be easily find out by using dimensional method. So next is time period. How to find a time period? The equation of time period. Okay. How to find the equation of time period? Simple pendulum system. Okay. So suppose in question, the problem is again, we know T depends, T is proportional to m raised the power a, L raised the power b, and G raised the power c. Okay, G raised the power c. So let me clear here. T is time period, T is time period, and m is mass, L is length and G is gravitational, ठीक है, acceleration, ठीक है. Here m is mass, L is length, and G is gravitational acceleration. Okay, so we have to find again the exact formula for T. We have to find the exact formula for T, and to find the exact formula for T, we have to find what is the value of A, B, and C. Okay, so let's remove this proportionality. If we remove this proportionality, then we have a constant value, which I will discuss just finishing the problem. M raised the power A, L raised the power B, G raised the power C. Okay, so K is a constant, it's just a number. Okay, so we just have to find the value of A, B, C in this equation. Okay, so here in left hand side, here T is a time period. So unit of time period is second, and the dimensional representation of time is capital T. Okay, capital T, the dimensional representation is capital T, is equals to, let's forget about K because it's just a number. We don't have any use of magnitude in dimension analysis. Now capital M, M is mass. So the dimensional representation of mass is capital M. Okay, M raised the power A. And here L is the length. Okay, Siddharth, L is the length. So, hello, are you there?
Yes, sir.
Siddharth, are you there? Are you listening me?
Yes, sir.
Okay, L is the length. So I just put L raised the power B, and G is gravitational acceleration. Okay, what is gravitational acceleration? I will discuss it later. What is G? But G is constant. You know, in our past classes you have studied what is G. G is gravitational acceleration. It is constant. It has a unit of acceleration. It has a unit of acceleration. So what is the unit of acceleration? Is L t minus 2 meter per second square. L t minus 2 raised the power C. Okay. So let's do little bit calculation. That M raised the power A, L raised the power B, and here L raised the power C into T raised the power minus 2C. Okay. Now next, here there are two terms of L raised the power B and L raised the power C. So if you multiply these two terms, then you will get a value which is M raised the power A, capital L raised the power B plus C, and capital T raised the power minus 2C. Okay. And in left hand side, the value is capital T. Now compare, if you compare, and here the only term is T. But so how you will compare? How you will get the value of, because here is M term, here is L term. Okay, so listen very carefully. I can write here M raised the power A and M raised the power 0 and L raised the power 0. Can I write?
Yes.
All of you agree now? Because M
Yes.
raised the power 1, L raised the power 0 is 1. Okay, so I can write M because you can multiply 1 easily in any equation. So M raised the power 0, L raised the power 0, and T raised the power here is 1. Okay. So from here, if you compare M raised the power A, M raised the power 0, the value of A is 0. Again, B plus C, L raised the power B plus C, here L raised the power 0. So here you will get a value B plus C equal to 0. And another equation is T raised the power 1, here T raised the power minus 2C. So here you will get the value minus 2C is equals to 1. Okay. So now your problem is solved. You get the value of A, which is 0. You get the value of B plus C, which is 0. And you get the value of minus 2C, which is 1. So here you can find the value of C, which is minus 1 by 2. And if you put this value of C in this equation, B plus C, if you put the value of C in this B plus C, so here you will get B minus 1 by 2 equal to 0. So here the value of b is equals to 1 over 2. So the value of a is 0, the value of b is 1 by 2, and the value of c is minus 1 by 2. These are the three values. Okay. So now you can use these three values in our equation. What is our equation? Our equation was t is equals to k. T is equals to k, m raised the power a, L raised the power b, and g raised the power c. So here k, m raised the power a, what is the value of a? A has the value 0. So here m raised the power 0, L raised the power b, which is 1 by 2. So L raised the power 1 by 2, and g raised the power c, which is the value of c is minus 1 by 2. G raised the power minus 1. So here we can have our formula for time period. T is equals to k, L raised the power 1 by 2, g raised the power 1 by 2. So this will be 1 by 2 divided by g raised the power 1 by 2. So if any quantity has power 1 by 2, so we can write in the form of square root. We can write it in the form of square root. So that will be basically k under root L upon g. Okay. Is it clear? And
Yes, sir.
by experiment, this value of k is a number, as I already told you. So this is t is equals to 2 pi under root L upon g. This is the correct formula. Okay. This is the correct formula. This is the correct formula. You don't need to write the value of k. I just write it because I'm just want to show what is the exact formula. So what is this formula? This formula for time period of a simple pendulum. If you put a simple pendulum, something like this one, if you hang out a bob with a thread, okay, so the time period of oscillation can be represented by this formula. T is equals to 2 pi under root. These are basically two famous examples. One is centripetal force and the other one is time period for a simple pendulum, to finding the relation among the physical quantities. Okay. So in today's lecture, basically I discussed from very beginning, I discussed what is fundamental unit, what is derived unit. Okay. And I discussed a lot of, first I discussed 7 fundamental units, 2 supplementary units. And after that, I solved a lot of derived units, a lot of 11, 12, I think derived units, all the basic and important derived unit I discussed. And after that, I discussed application of dimensional analysis, in which I discussed 3 major applications. Okay, 3 major applications. Okay, first we find the correctness of equation is correct or not by using dimensional analysis. Second, we discuss what is conversion of unit. We convert from
physical
SI,
quantity from one system to unit to other.
To unit system, SI to CGS. And the third application, we find the relation among the physical quantities. Okay, so this is all about the today's lecture, in which I finished the dimensional analysis. Okay.
Yes, sir.
Okay, sir.
Okay, so okay, let's close this session. If you have any query question, then please ask. If you don't have any question, so we can close our session. Okay.
Yes.
Okay, see you guys.
Thank you so much, sir.
Okay.
Thank you, sir.
Okay.